Okay, so let's look at question 5. It says an object of mass 200 kg is orbiting the Earth at a distance d from the Earth's surface. The weight of the object at that position is 10% less than its weight on the Earth's surface. Then 5.1 says state Newton's law of universal gravitation in words. For 2 marks, let's run quickly to that. Say Newton's law of universal gravitation states that every particle in the universe attracts every other particle with a gravitational force that is directly proportional to the magnitude of the product of their masses and inversely proportional to the square of the distance between their centers. Then 5.2 says calculate the distance d from the Earth's surface at which the satellite is orbiting. Right, so from the Earth's surface, and then we are told here that the weight of the object at that position is 10% less than its weight on the Earth's surface. Right, so now we understand that the satellite is at some distance apart from the Earth's surface, and then now we are required to calculate the distance. But then let's start by this. Let's calculate the weight of the satellite on the Earth's surface. So that's W is equals to mass times the gravitational acceleration. So if the satellite was still on the Earth's surface, then its weight would be 200 multiplied by 9.8, and then we would have, punching that in your calculator, we would have 1960 newtons. But now that it is at a particular distance away from the Earth's surface, then we are told that at that position, this satellite is 10%, its weight is 10% than what it is on the Earth's surface. So what should we do? We should subtract the 10% from this. So we can do that by first finding the 10% of this weight. So multiply by 10 over 100, and then, so let's write nicely. So we have 1960 multiplied by 10%, that's 10 over 100, and then we have 196. So now what are we going to do with this 96? We subtract it from here because remember it's 10% less than, right? So we say 1960 minus 196, and then we find the weight of the satellite at that particular height. So it's 1764 newtons. So this is the weight of the satellite when it is a distance d away from the Earth, right? So now we are required to calculate that distance. Now the formula that we use for this one is obviously g, so equals to m1 m2, and then we can say over r squared, right? So this is the square of the distance between the Earth's surface and the satellite. So what is the weight that we have? It's 1764, and then the g, remember, is a constant of 6.67 multiplied by 10 to the exponent of negative 11. And then what is mass 1? We will take it as the mass of the satellite, and mass 2 we will take it as the mass of the Earth, because remember here we are having an interaction between the Earth and the satellite. So that's 5.98 times 10 to the exponent of 24. So this value is the mass of the Earth. It can also be found on your data sheet. Then here we have r squared. So to calculate this, we only need to swap this, right? So over 1 here, can just cross multiply here, and then make r squared the subject of the formula. Then we will have 6.67 multiplied by 10 to the exponent of 11, and then 200 multiplied by 5.98 times 10 to the exponent of 24, and then all that over 1764. Then to get rid of the square here, we can just square both sides like this. And then the r, so let's continue from here. The r will now be equal to 6.725. So I'll just round off to 3 decimal places, times 10 to the exponent of 6 meters. Right. But then remember, the question is saying calculate the distance d from the Earth's surface at which the satellite is orbiting. Right. So now we will then consider that this one, if it is out of the Earth, that means now we have the distance. So this is the satellite. If I can just draw here, this is the satellite and this is the Earth, right? So what we have here is the distance from the Earth's surface. So from the Earth's surface all the way to the satellite, right? But then now the distance that we are actually looking for here is the distance between this outer part of the Earth and the satellite. So what should we do in order to calculate this distance? We will note that this distance here also includes the radius of the Earth, right? So we don't want our calculation to form we don't want our value to be to form part with the radius of the Earth, right? So we only want this distance without the radius of the Earth. So now to calculate the distance, we'll say distance is equals to this radius here that we have, but then minus the radius of the Earth, right? So our distance d will now be equals to 6.725 multiplied by 10 to the exponent of 6 minus the radius of the Earth can also be found in our data sheet, and it is 6.38 times 10 to the exponent of 6, and then the d is equals to 3.45 times 10 to the exponent of 5, and then meters. So that's your solution. Let's write this one neatly. So that's 10 to the exponent of 5. So, yep. Okay, then 5.3 says the object is moved to a new position where the distance from the center of the Earth is twice the radius of the Earth, right? And then they say write down the mathematical relationship between the weight of the object and the distance at which it is placed from the center of the Earth. So to write the relationship, 1 mark, it's pretty easy. You just go weight is inversely proportional to the square of the distance between the masses of these objects, right? So the relationship is 1 over d squared, or you can write it as Fg inversely proportional to the square of the distance. Okay, so 5.3.2 says determine the weight of the object at the new position. But what are we told here? We are told that the object is moved to a new position where the distance from the center of the Earth is twice the radius of the Earth. So now, in order to successfully answer that one, let's first write out this equation for universal gravitation. And then we are told that what is changed here is the distance, or rather the radius of the Earth. So now to indicate, we are told that the distance is twice the radius of the Earth. So this is 2 multiplied by what? By r, right? So because the distance is twice the radius of the Earth, so the r here, we take it as the radius of the Earth, and then this is 2 multiplied by r, and we still have this square, right? Then this is 2 to the exponent of 2. It will give us 4, but then we have 1 from the numerator here, so this will be 1 over 4, and then g m1 m2 over r squared. But then now you will note that the gm1 m2 over r squared represents the weight, right, or the force, right, or the force of attraction between these objects. So this is F. So we can now write out this one. We say the F nu, or the new gravitational force, is equals to 1/4 of the old gravitational force. Now remember, when we first calculated, we calculated the weight to be 1960 newtons, right? So this was before the satellite was taken out of the earth, right? So its weight was 1960 newton on the earth's surface. So this is what we are going to use. So we'll say 1/4 multiplied by 1960, and then we find the new gravitational force to be 490 newtons. And that's it. Awesome.